we talk about bounding L-torsion class groups of Hamiltonian number fields of arbitrary.
Thank you for saying my entire name and the entire title. I appreciate that. And also thank you to the organizers for the invitation. It's my pleasure to be here and tell you about some new things that I've been working on since I've been at Duke. So before we get into what all these things in the title mean, I should motivate why someone would even look at a class group. And as a lot of things do, that means we're going to talk about Gauss. So just to motivate this idea a little bit, first just considering binary quadratic forms. So a binary quadratic form is a homogeneous polynomial of degree 2 and 2 variables, which I can represent this way. And one might want to talk about two forms being equivalent. And so two forms are equivalent if there is an admissible change of variable action through SL2Z that transforms one of the quadratic forms into the other. And this can be made precise like I've got here on the board. So Gauss was interested in classifying the binary quadratic forms with a given discriminant. And to do this, he formed what's called the class group. And this is a group of equivalence classes of binary quadratic forms with a given discriminant. And the group action is what is referred to as Gauss composition. And Gauss showed in particular that for any given discriminant D, there exists only finitely many equivalence classes of binary quadratic forms. OK, so what does this have to do with number fields? Well, on the other side of things, you can think about a quadratic number field K. And now we want to talk about what it means for two non-zero ideals to be equivalent. And so they're equivalent if you can find an R and S in the ring of integers OK, such that this relationship holds. So to each binary quadratic form that I had given on the previous slide, one can associate an ideal of OK in the following manner. And this association is very strong. And so, for example, if on the one side, if you have an equivalent binary quadratic form, this corresponds to equivalent ideals. And the group action, this Gauss composition, corresponds to the multiplication of the equivalence classes of ideals. And so you can define the ideal class group now from the number field side of things. And so we're going to denote the ideal class group. So here I'm still talking about quadratic K as CLK. And the size of this is called the class number. And so in this case in particular, because of this correspondence to binary quadratic fields in the work of Gauss, you can see that this class number is finite. OK, but you don't have to just stop at quadratic number fields. You can define the class group for number fields of higher degree. And so here we see that the way we define this is we take the quotient of the group of fractional ideals of K and mod out by the subgroup of the fractional ideals, which are the principal ideals. And this defines the class group of K. And again, we're going to use the same notation. Whatever the size of this group is, we'll call it the class number. And one thing to point out is that if the class number is equal to 1, then that means that OK is a PID, which implies that OK is a UFD. And actually, in this case, the other implication works as well, because OK is a Dedekind domain. But the point is that the class number is, in a sense, a measure of how far off a field is from having unique factorization. OK, so if we want to understand the size of the class group then, notice that Landau observed that the following upper bound holds for the class group. Here, dk is just the absolute discriminant, k over q. And R2 is the number of pairs of conjugate complex embeddings of K. Now, and in particular, I want to point out, too, that the class group so it's finite, but it's also an abelian group. So you can start talking about its Pili-Stilo subgroups and things like this. And so this motivates the idea of looking at the L-torsion subgroup of the class group, which is what I'm going to be interested in. So for any integer L, you can define the L-torsion subgroup of the class group in the following way. So we're looking at all of these ideals in CLK that satisfy this property for the given L. L is fixed. And so a natural question you might ask is, well, what's the size of this L-torsion subgroup? And you might ask that for a specific K, or you might ask it over an appropriate family of fields K, what kind of bounds can you get? Okay, so I'm going to outline some of the progress that's been made on understanding the size of this subgroup. It's not going to be exhaustive, but I'm going to try to highlight some of the current status of where we are. Okay, so before I talk about all the great results, we should at least put things in context. What's the trivial bound? So the trivial bound of the size of this subgroup is, of course, the size of the group it lives in. And from what we saw on the previous slide with Landau, we can see that the trivial bound on the L-torsion subgroup is going to be this discriminant dk to the 1/2 plus epsilon. So if we can beat 1/2 plus epsilon, then we've beaten the trivial bound. Okay, so there's the conjecture. So I'm sorry, I didn't tell you what the conjecture is. So the trivial bound is what I have before, is that you should have a 1/2 plus epsilon, but we actually think that it should be much smaller in this sense, is that this should be bounded above by dk to the epsilon. All right, so we think that we should be able to get rid of this entire 1/2. And this has been recorded, this conjecture has been noted in different settings with different motivations, and I've listed some of them here. Okay, so we'd like to get an epsilon, and the trivial bound is the 1/2 plus epsilon. Okay, so Gauss took care of the case where k is a quadratic number field and L is equal to 2, and proved exactly what we hope to be true, that the size of this two-torsion subgroup for a quadratic field here is dk to the epsilon. All right, so let's see where we are now. So, and again, these are some results that trump earlier results, but it's just to kind of tell you where we are now. So in 2007, Ellenberg and Venkatesh showed that, so first, if you have a number field of degree 2 or 3, then you can get the following upper bound on the 3-torsion subgroup of 1/3 plus epsilon. And also that if the number field is degree 4, but it's non-D4, meaning that its Galois closure group is not isomorphic to D4, then we can get this upper bound. And so they shave off from 1/2, 1/168. Okay, and then very most recently, Bhargava and I know Frank is here, so let's just say Frank is one of these others that's listed here. I hope I haven't missed anybody else that's in the audience, because I don't want to hurt anyone's feelings. Is that if you have a number field of degree greater than 2, then there exists a delta that depends on this degree, and so that you can shave off a power here. And this is for the 2-torsion subgroup. And these results are really nice because these are for all of these number fields K. You can make this statement in the appropriate setting. Okay, so what do you get if you assume GRH? All right, so Ellenberg and Venkatesh also showed that if you assume the generalized Riemann hypothesis, then for any degree n field and any L that's a positive integer, you can shave off a power of 1/2L times n minus 1 off the trivial bound. And this is what you get if you assume GRH. Okay. Now, maybe you can say something else. If instead of saying you want the result to hold for all k, maybe you can say I want it to hold for all but a possible exceptional family that's very, very small, zero density. And so in 2000, Sounds showed that if L is prime, then for all but a possible zero density exceptional family of imaginary quadratic fields, then you can get a non-trivial upper bound on the size of this L-torsion subgroup. And then in 2014, Heath, Brown, and Pierce showed that if L is greater than or equal to 5 and it's prime, then we can get this for imaginary quadratic fields as well, with a little bit more taken off. Okay, so now that we have kind of allowed ourselves in this setting where we're going to say maybe we can't do something for all k, but we can do something for all but a set of zero density of k, fields of k, what can we say? And so the current kind of all-encompassing statement is a very recent result of Ellenberg, Pierce, and Wood, who've shown the following. So they've shown that if you let L be greater than or equal to 1, and k is a degree 2, 3, or 5 number field, then for all but a possible zero density exceptional family of fields, we have this upper bound. And I've been showing you a lot of upper bounds. but this is the one that is given assuming GRH by Ellenberg and Venkatesh. So they're recovering this GRH bound from before without assuming GRH. And then in the case where the degree of the number field is 4, the same bound applies as long as K is non-D4. Okay, so what I'd like to talk about now is how could you get a bound of this shape for maybe degrees higher than 5 and without assuming GRH. And that's what I'm interested in doing. Okay, so here is kind of the general shape of a result I would like to be able to prove. And then we'll talk about what all these things mean in detail and what we can actually do in a few minutes. So here's the general shape of the end result that we want. So let G be a transitive subgroup of Sn, and the order is at least 2. And we're going to define a family of fields, K over Q, with the following specifications. The Galois group, or the Galois closure of K, is going to be G, that subgroup that we fixed from the beginning. The absolute discriminant, d sub K, is going to be in the range 0 to some large x. And we'll also have a restriction on the tamely ramified primes in K. And we'll see at the end this is a necessary condition. And so the idea is that if we define our family appropriately, then what we would like is to be able to say that for all but a positive zero density exceptional family of fields in f of x, every single one of the K within this family satisfies for every integer L the bound as we see here. And again, this exponent is the exponent from the Ellenberg-Venkatesh result, assuming GRH. And there'll be some caveats along the way. So as long as G, certain conditions there are in G might have to be held, and we might, in certain cases, have to assume other conjectures, but we won't assume GRH. Right? So we're trying to see what can we do without assuming the Riemann hypothesis. Okay, so let me tell you 2 of the results that we are able to prove. But each case is different depending on G, so I'm not going to list every single one of them, but just to kind of give you an idea of what we've got. Okay, so the completely unconditional result is for G a cyclic group. So if G is a cyclic group, then we'll define the family so that, well, K is already Galois, so the Galois group of K over Q is the cyclic group. The discriminant is within the appropriate range. And the restriction on the tamely ramified primes will be that all the rational primes that ramify in K are totally ramified. And then we get the result that we want for all K within our family except for a possible exceptional family, zero density family of fields, we get the bound that we want. And moreover, it's nice to note that if n is prime, then all the fields in our family satisfy this bound. So the exceptional set is empty. All right, so this is one of the results that we were able to prove when G is cyclic. On the other side, let me show you what the statement looks like when G is isomorphic to Sn. Yeah, so we do have qualitative and quantitative versions of these theorems. And so we'll be able to say what the size of that family looks like. Yeah. Okay, so if we have Sn, then the statement setup is similar. The way that we define our family is that we'll restrict to K with square-free discriminants. This is actually a condition on the tamely ramified primes, but we can state it in this way. Then there's some conditions that we'll have to assume. We'll have to assume what's called the strong Artin conjecture and something that's called the discriminant multiplicity conjecture. And then we'll get the upper bound that we want. Now I'll talk about what these conditions mean and things like that, but it's just to kind of give you an overall shape of what we're able to prove. And again, just to point out, the condition that our discriminant is square-free includes a positive proportion of discriminants, and it is equivalent to a set ramification type for the tamely ramified primes. Okay, so these are 2 versions of things that we can prove, and in addition, we have theorems if G is a simple group and if G is a dihedral group dp for p an odd prime. And then within those conditions, there are different ramification restrictions that you have to make, and there might be different conjectures that you have to assume, but we won't assume GRH. Okay, so let me tell you what I'd like to do in this talk now that I've kind of tell you what we can prove. So the method that we have created to solve this problem is new. It's different from the methods for the previous results that I mentioned. And so it takes a lot from different fields. So there are aspects of algebraic number theory, analytic number field, or analytic number theory, and class field theory as well. And so what I'd like to do is just give a sense of what the method is. And so I would like to kind of give kind of a broad talk so we can see how the pieces fit together. So in order to motivate it, first I'll show how you could go about getting an upper bound if you assume GRH. Then I will describe the overall structure of our method, which allows us to circumvent, assuming GRH. And then kind of along the way, when it's necessary to introduce certain conjectures or new key players into the method, I'll introduce them as they come, instead of giving you a whole bunch of slides before on L functions and things like that. So I just would like to point out, since we're going to just describe the overall structure of our method, I will say that rigorously stitching together the pieces in our method is delicate, and we're very careful to do so in our paper. So I just want to make sure that's clear, since I'm going to be a little bit more talking more generally today. Okay, so let's first talk about how one might get the bound assuming GRH, because the starting point is the same as our method. Okay, and the starting point is the following theorem of Ellenberg and Venkatesh. And we'll just take this as a black box. All right, so here's the statement. Suppose big K over little k is an extension of number fields. And let's set delta to be less than this number right here. That's going to be fixed because we're going to fix L as well. And suppose that you can find m primes in the ring of integers of little k, where the norm of these primes is small in this explicit way. And we want them to split completely as well in big K. All right, so Ellenberg and Venkatesh show that if you meet these assumptions, if you can find this many primes of small norm that split completely in K, then you can get the following upper bound on the L-torsion subgroup. And so the question then is, okay, so the whole point, if I want to shave anything off of the trivial bound, which is right here, then I've got to find some primes that split completely in K and that have small norm. And so the question is, how do you go about finding primes that split completely in K with small norm? And the answer is you appeal to a Chebotarev density theorem.
Where is delta in the conclusion?
Yes, it's right here in the norm.
You find these primes, and then for any delta that you can do that, then you get the same bound?
So the number of primes that we end up getting will include delta. Will depend on delta.
Okay.
Yeah. Okay, so we want to find small primes, and we're going to do that via a Chebotarev density theorem. And the Chebotarev density theorem that Ellenberg and Venkatesh show you can apply to get the result is one that's due to Lagrange and Adlishko. And so in order for me to state it, let me tell you what some of the pieces are that show up in a Chebotarev density theorem. Okay, so let's let L over little k be a normal extension with Galois group G. And what we would like to do is we'd like to count the prime ideals in the ring of integers OK that are unramified in L and whose Artin symbol corresponds with some targeted conjugacy class that you want to hit within G. And also, we want the norms to be small, right? Because we're trying to find primes of small norm. And so, in general, the Chebotarev density theorem shows that prime ideals are equidistributed amongst the conjugacy classes in G. And since we're interested in finding primes that split completely, then we are going to try to prove it. We would like to have a Chebotarev density theorem where we can take C to be the trivial class. And this will correspond to primes that split completely. All right, so the effective Chebotarev density theorem that is necessary to prove this sort of result, we can take the following due to Lagrange and Adlishko. Okay, so let's look at the setup. We have a normal extension of number fields with Galois group G. Capital DL will be the absolute discriminant of L, and N sub L will be just the degree of the extension. Right, and so Lagrange and Adlishko proved that there exists an effectively computable constant C0, such that if you assume the generalized Riemann hypothesis for the Dedekind zeta function ZL, then no matter what conjugacy class you want, you can get the following error term in your Chebyshev density theorem. And so the point here is that because of their statement, you can choose x in an appropriate way so that you can find at least this many sufficiently small primes in OK that split completely in K. All right, so the point is that you have to be able to find, so the bound in your effective Chebyshev density theorem has to be strong enough, and you have to be able to make this choice of x within the range that the theorem is proved as well. All right, so this is how the pieces then fit together. So you start off with your Ellenberg Venkatesh black box, and we're looking for small primes that split completely. We find those via an effective Chebyshev density theorem. And the one that I've got quoted here assumes GRH. And so then if you assume GRH, you can put this in, and you get this upper bound that we've claimed before. Right, so these are kind of like the key steps that you have to prove in order to put these pieces together. All right, so what I would like to do is remove the assumption on GRH. And there's going to be some cost for doing that, for getting rid of GRH. And so the cost is going to be that will prove the result for all but a zero density family of fields. OK, so let's look at kind of the flow of this method. All right, the starting point is the same. We're going to start off with this result of Ellenberg and Venkatesh. And then we're going to prove an effective Chebyshev density theorem that assumes some other non-zero or some other zero-free region, but not the one that you get from GRH. All right, so we won't assume the Riemann hypothesis in our effective Chebyshev density theorem. We'll just assume that the Dedekind zeta function satisfies some other zero-free region. Well, if we do that, then we have to show that the assumed zero-free region is obeyed by most fields in the family. And what I mean by most fields is that the Dedekind zeta function of those fields, of the Galois closures of those fields, obey the zero-free region. And then there'll be a very subtle point that we'll have to take care of. We'll have to be able to control the potential propagation of bad fields whose Dedekind zeta function doesn't want to satisfy this zero-free region. But once we do that, if we prove our theorem with a sufficient error term, and in a small enough range of x so that we have the freedom to take x wherever we'd like, we'll be able to move back up here and say, without assuming GRH, we can conclude that this upper bound holds, again, for all but a possible zero density set of family of fields. OK, so we don't have to do anything new for Ellenberg and Venkatesh, because that's our starting point. And so the next thing on our list, then, is to see what this effective Chebyshev density theorem looks like. OK, so now it's time to talk about a Dedekind zeta function. All right. So Dedekind zeta function, so we'll be considering L Galois over little k. And one can define the Dedekind zeta function attached to L in the following way. So we have a Dirichlet series over the ideals of OL, and an Euler product over the prime ideals of OL. And the Dedekind zeta function has analytic continuation, a simple pole at 1, and so forth, all the nice things that you need out of a good, well-behaved L function. OK, so in general, when L is Galois over K, we know how the Dedekind zeta function of L factors. So since I've got L defined over some number field K, then the way that I can factor the zeta of L is in terms of Artin L functions. So when I have an irreducible trivial representation of G, that Artin L function is the Dedekind zeta function of little k. And then I'm just going to group together all the other Artin L functions that depend on the remaining irreducible representations of the Galois group. G, yeah, thank you. OK, so that typo will propagate. OK. OK, so if you've not seen these things before, and you might think, oh, what does this look like? So in certain cases, you can just read SARE or go to lmfdb.com and like write down exactly what the Dedekind zeta function looks like. So the next slide is for people who look at this and think, what in the world is this? It's just something tangible. I'm not going to go through what all these representations are, but I just want to point out that you can actually explicitly write this down by looking up some data online. So for example, if you want your Galois group to be S5, then it's known what all the irreducible representations of G are and what their dimensions are. And so then you can just write the corresponding L function for each representation as so. And the power that appears is the dimension of the representation. And again, in this case, you might say, well, in the previous slide, you had a little k, but now you don't have one. Well, now I've taken little k to be q, and so the trivial representation gives you the Riemann zeta function. OK, so in general, we're just going to hold on to this factorization. But if you're new and you're learning stuff like this, you can get a handle on it by just looking up some specific data. OK, so what do we want? So we want a zero-free region for the Dedekind zeta function ZL. And again, notice that we have this factorization. So what we're going to do is we're going to have a blended zero-free region. So first, what we're going to do is we're going to look at an assumed zero-free region for this Dedekind zeta function z sub k. Now, the only thing that we're going to assume here is that this Dedekind zeta function doesn't have an exceptional zero. Ultimately, we're going to take little k to be equal to q, and so this assumption will go away. So, but if I go ahead and get rid of the possibility of an exceptional zero, then I can just use this following standard zero-free region of the Dedekind zeta function. So this is like taken straight out of Ivanez-Kowalski. So usually the statement says that this is the zero-free region except for a possible exceptional zero, but I'm going to assume that that doesn't happen. OK, so that's the zero-free region I'm going to have for this factor. And for the rest of the factors, just the quotient of ZL and ZK, which can be written as this product of Art and L functions, but can also be stitched back together to give you one big L function that can be factored. What we're going to assume is the following. We're going to assume that there exists a positive delta less than a fourth, such that the quotient, meaning this entire product and the factors therein, are zero-free in this box. There's going to be a reason why we choose this. Right? It's not out of thin air. But just to give you an idea of what the zero-free region looks like, here is a not well hand-drawn picture by me on my iPad. Of course, I'm only looking in the upper half plane, and I've blown things up so you can really get an idea of things. But the point is that the zero-free region for the Dedekind zeta function is this curve here. And then the box is the box that I assume for the rest of these Art and L functions. And so what's shaded in very light blue that you might not be able to see is the assumed zero-free region for the entire function. And we're going to make things, if you're already worried about, well, wait a second, how do you know where this intersects? We're going to make sure all our discriminants follow certain bounds, so this is the picture that we have. OK, so this is the assumed zero-free region that we take for ZL. And by assuming this, we can prove the following effective Chebotarev density theorem. OK, so this setup is the same as before. The only difference is that we're going to assume that ZL obeys the assumed zero-free region. And again, I'm just going to point out that we assume that zeta k didn't have an exceptional zero. And then this is the effective Chebotarev density theorem that we can prove. And we have a lower bound for x for which this is valid. So let me point out a few things here. First, here I say that DL is sufficiently large. That's made precise in our work. And this constant c is an absolute constant. All these little c's are parameters that depend on delta, the degree of little k, the degree of big L, the discriminant of little k, the size of g, and we make all of that precise. But I'm just saving you from seeing anything grosser than what I have here. But what's really important, well, I'll just say that. So anyway, all of these hand-wavy things about sufficiently large and what these parameters are, we make all of that explicit. OK, so the way that we prove this, I'm not going to prove it, because I'm just giving you an overall feeling of how this works. But we actually go back into the inner workings of Lagarish and Eliashko's proof of their effective Chebotarev density theorem. one of the ideas that you have to do there is this trick by Turing, where you have Art and L functions that are hard to understand, so you instead factor the Dedekind zeta function into Hecke L functions, and you show how you can bridge these two things. And we go back into the fundamentals of their proof, inserting our assumed zero free region in a key location. Okay, so this is our effective Chebyshev density theorem. And so now, as we're looking at the overall scope of our method, the next thing that we have to prove is that most of the number fields within our appropriately defined family have Dedekind zeta functions whose Galois closure actually satisfies this zero free region. And this is kind of a loaded bullet point. So let's first talk about what we mean about an appropriate family. Okay, so for the rest of the talk, I'm going to take little k to be q. I don't have to take it for much longer. I could keep talking about little k being little k. But ultimately, we're going to have to take little k to be q, so I might as well do it now. All right? But the one thing to note is that our theorem that I did state before works over arbitrary little k. Okay, so here's our picture. We're going to define a family of fields k that satisfy the following picture. So we're going to fix the degree of k over q. And now L will denote the Galois closure of k. And whatever the Galois closure is, we're going to fix that as well within our family. And we'll fix a ramification type for all the tamely ramified primes in k. Depending on what G is, that restriction is going to be different. Now, one thing that we need to be able to do is we need to be able to understand how many fields we have in our family. And so we can make one more restriction where we say we're going to take fields k that live in our family and only consider those whose absolute discriminant is in the range 0 to capital X. And we need to be able to find appropriate bounds on the size of this. And there are lots of cases where, depending on your Galois closure, you can measure this. For the point of the talk, I'm going to point out some of the situations where it's very helpful, but I'm in no way going to be covering all the known results in this direction. So let's say, for example, for S3, S4, and S5 fields, then bounds for this family are known. And here, what I've gotten here, so I've got a K tilde Galois closure. You can also think of it as L from the previous slide. These are results when the Galois closure is over little q. There are also, for each of these, for the first two results, corresponding cases when q is equal to little k. And there are results when you have A4 is your Galois group, or you have nilpotent groups. There are lots of results in this vein. Now, for G being cyclic, we can compute sufficient lower bounds on the size of our family. And maybe what I mean to say is Melanie Wood can compute this. Okay. If G is equal to Sn, then there are already known lower bounds on the size of this family. And they're actually pretty weak, but the size of our exceptional family is so small that these weak lower bounds suffice. Now, in other cases, in other settings, one might have to assume the following conjecture. And this is a weak form of Malo's conjecture. And what this does is it tells you, gives you appropriate bounds, upper and lower bounds, on the size of this family f of x in terms of this number ag, where this is a number between 1 over n minus 1 and 1, and it depends on the index of G. So what I mean to say is that in other cases for your Galois group G, there are conjectures on the books for how this should behave. But even in terms of this Malo's conjecture, we need lower bounds, is what we need for our method to work. And you don't even have to get something as good as what Malo has in some cases. OK, but we need to be able to know how many fields we're counting to begin with. And if G is cyclic, then we can do this. And we do this ourselves. And if G is Sn, then there are already known lower bounds that work for us. OK, so let's just kind of check in where we are. We've defined a family of fields and a collection f of x where the only now differences that we're restricting where the discriminant is in a range. In some cases, we know how to compute the size of f of x, and in other cases, we might have to assume that we can via Mullis conjecture. And so we want to show now, back to what we were really trying to do, is show that the zero free region is obeyed by most of the L functions in our family. And so to do that, we have to introduce automorphic L functions. OK, so let pi be a cuspidal automorphic representation on GLM. And I already used rho to talk about Galois representations. So I'm going to be very off script and use an S to denote a 0 of these L functions instead of a rho, which is more common. But let's let beta plus I gamma denote a 0 of the corresponding automorphic L function ls pi. And let's say that we want to count how many zeros this function has in an appropriate range. So maybe the real part is greater than some alpha, and the imaginary part is at most t. So Kowalski and Michel have given a bound on the number of zeros of these L functions that holds on average for an appropriately defined family of cuspidal automorphic representations. So let me show you what that looks like. So in this 2002 paper of Kowalski and Michel, they build a family of cuspidal automorphic representations, and they satisfy a prescribed set of conditions. I'm not going to go through all of the conditions. But if you define their family appropriately, then on average, you can count how many zeros there are within this family of L functions. And the point here is that when you apply this counting of zeros to the cuspidal automorphic L function, then you obtain a zero-free region of the shape that I described of my assumed zero-free region earlier. And this will work for all but a possible zero-density subfamily of the L functions within the family. Now, if you look at this, this is the result I would like to apply. But there's some obvious problems with the setting that I'm in and the setting that this is. One of the problems is that I'm working with art and L functions, which aren't known to be automorphic in general. Okay? So if the Galois representations are degree 1, then these are already known to be automorphic, but in general, they're not. So what I'm dealing with here is, so I've got my zeta L, and remember I took little k to be q, so now I've got the Riemann zeta function, and I've just divided it on the other side. And so these are all the art and L functions that I was dealing with to begin with. OK, so this is where we assume what's called the strong Artin conjecture. In other places, it's called Langland's reciprocity, to tell me that each one of the L functions within my factorization corresponds with an automorphic L function. OK, so I might have to make this assumption in certain cases because the Michel-Kowalski result applies to automorphic L functions, right? So I have to know that that's what I'm dealing with. So I need to know it, so I'm going to apply it for each one, and this is my other issue that I've got. All right, so the other issue is that Michel and Kowalski's result only applies to cuspidal L functions. But I've actually got what's known as an isobaric automorphic L function. All right, it's reducible. All right, so we've got to figure out a way to adjust the Michel and Kowalski result to apply to isobaric representations so that I can apply it to each one of these. And actually, and to answer your question more precisely, we're going to apply it, we're going to group all the same ones with their powers and then apply it that way. OK, so let's just see what that looks like, how we're going to do this. So if I factor zeta L over zeta in the following way, then I'm going to create a subfamily of L functions. And this subfamily script L sub j is going to correspond to one of these columns of L functions. So you can imagine you've got this family of Galois closures, and you write down their Dedekind zeta function, and then you write out its factorization, and you put some ordering on the representation so you can say, you know, maybe this one's the sign representation, and the next one's the standard representation, something like that. And so you're going to denote within the columns that you would get from writing down all the L functions a subfamily. And so what we'll do is we'll apply Kowalski and Michel's zero-density result for cuspidal automorphic L functions to just the L function that shows up within this family. And so what we can do then is conclude that a zero density set of exceptional L functions can potentially fail to have the desired zero free region. And stitching all of this together is delicate. But we make many efforts to do so very carefully. But the key technical point now is that for each one of these J's, we have to quantify how many Galois closures L in the family could contain an exceptional L function within the family. Because we don't want to end up having so many that our exceptional set is not so exceptional anymore, right? That's too big. Okay, so this is what I mean when I say we have to control the propagation of bad fields. All right, so the following result is very, very helpful and sheds light onto why we have to let little k be q at the end. So this is a very recent result of Kluners and Nicolai. And they've shown that if L1 and L2 are finite Galois extensions, and you have a faithful character of their corresponding Galois groups, that if their L functions coincide, then the number fields themselves coincide, as do these representations. So yesterday when I saw Maria's talk, I immediately perked up, right? But this is on the side of these Galois extensions. And so the point here is a point that the authors make explicitly in their paper is that if little k is not equal to q, then the R and L function need not detect identical number fields. So you could have the case that the L functions coincide, but the number fields are different. And they give explicit examples to show this in their paper. Okay, so what we do, we've got a problem about L functions, and we find a way to rephrase the question in terms of number fields. And we can reduce this issue to counting number fields F that could probably that can arise as k varies. And the way that we can restrict to make sure we don't have too many of these overlapping number fields that contribute to our exceptional set and therefore make it too large is we have to control what primes can divide the discriminant of big K. All right, so just, I don't have it written here, but big K is somewhere in between Q and L. L is its Galois closure. And so what we have to do is we have to restrict to inertia types that one can still generate all of the Galois group, so we're not missing any of the Galois group, but also control the propagation of bad fields. And so depending on the number fields, the Galois closure that you're in, this looks different. Right? So you have to go through and calculate which conjugacy class to restrict to. Okay, so in certain cases as well, we might, in order to control this propagation of bad fields, we might have to assume something of the following form, which is referred to as the discriminant multiplicity conjecture. And that's that the number of degree D number fields with a given fixed discriminant is at most d to the epsilon. In fact, we can assume something a little bit weaker than this, but then we're getting more technical. So one thing to point out, if you're familiar with this problem, is that if you assume the discriminant multiplicity conjecture for all degrees d, then you can actually get the L-torsion, the full conjecture for the L-torsion bound. But that's not what we're doing, so this is a subtle point. We're assuming it just for one case, for one degree, and getting the bound for all L. All right, so in case anybody was upset. And again, having Melanie Wood as a co-author is really nice. We don't have to assume this for cyclic fields because she's able to calculate, do all the counting that we need unconditionally. Okay, so in conclusion, just to look at our method here, what do we have? We start off with the Ellenberg and Venkatesh black box, where we have to count primes of small norm that split completely in L. We're able to count the number of primes that we need by proving an effective Chebotarev density theorem that doesn't assume GRH and has a sufficient error term and a low enough threshold for the allowable x so that we can get the number of primes that we need. we then show that the assumed zero-free region is obeyed by most number fields by appealing to this result of Kowalski and Michel, which we have to adapt for isobaric representations. And then on the class field theory side of things, we control the propagation of certain bad families within a field. And this is a situation where we then have restrictions on what Galois groups we can take, because in some cases we can control this, in some cases we can't. All right, but once we've done that and we're in the appropriate family, we can get enough of the small primes we want to feed back into the Ellenberg-Venkatesh method to get the GRH found without assuming GRH. And just as a reminder, one of our examples of one of the theorems we're able to prove is this for all degree SN fields, where we have a restriction on the ramification type that corresponds, as another way you can phrase it is that the discriminants are square free. We assume the strong Artin conjecture. Remember, that's necessary to apply Michel-Kowalski, Kowalski-Michel, and the discriminant multiplicity conjecture to get the upper bound that we want. And happily, in the case of cyclic fields, everything is unconditional. So one thing that I would like to say before I close is that, in a sense, the main result of this paper is this method, is this framework of how to apply Michel-Kowalski to these reducible situations to get these sort of zero-free regions that you might want. And so there are other situations that we're looking at applying this. And these are just some examples of a few things that we can do within this new framework. Thank you. Yes.
So what can you say about the size of the exceptional set? So for example, if you wanted to give an upper bound for the average of the L bar, is the exceptional set sufficiently small that you don't have to worry about it?
Yes, and so we have statements for each one of our theorems to describe the set. Off the top of my head, I'm not going to be able to recall to you what these look like, but we are careful to give alternate statements of our theorems that explicitly point out this point. Yeah, Frank.
So you mentioned that in some cases you assume a weak form of Mallet's conjecture.
Yeah.
Could you please say again what goes wrong if you don't have this?
So the issue is that, so maybe I can just say without finding the slide, we have to be able to control how big and how small our family is, and we have to be able to control how many possible bad families we have within it. So we have to have these bounds so that we can compare things in a pretty explicit way. But the size of our exceptional set is so small that we don't really need the full force of Mallet's conjecture in several cases. So Mallet has a result on SN fields that's the lower bound on the size of the set is pretty weak, but it's sufficient for our cases. And I can show you more detailed things if you'd like. Yes, Karen. Oh, okay, so we were happy that so a long time ago we thought that we might have to restrict to something like that. And we found a way that we didn't have to do it. So I think that maybe it might be now nice with fresh eyes to go back and look for some of the cases we weren't able to handle if that restriction would help. So I think that's a great idea. But originally we thought we might have to restrict to something like that, and we found a way around it. Yeah, Tim.
Could you say a couple of words about how you go about counting cyclic fields? Is it anything to do with Wright's argument for abelian extension?
So the idea is that so what we prove is we prove a lemma on how the discriminants, the exponents, the primes within the discriminant of K and its Galois closure can change. And so we have to make sure, we have to control the primes that so if you're tamely ramified up top, then you're tamely ramified down below, but the other direction is not the same. And so if you restrict primes, for example, the SN case where I said that the discriminants have to be square free, this is equivalent to saying that the tamely ramified primes have to live in the conjugacy class of transpositions. And so what we do is we have a framework to calculate which of these primes will stay ramified up above by restricting to these certain conjugacy classes.
I'm asking about counting cyclic. I'm trying to ask about whether you count, how you actually go about counting extensions which have cyclic Galois group.
I will reframe to Melanie for that.
Okay.
Yeah, I know that she's able to do it, and I'm still learning class field theory to understand her arguments.
Okay.
Yeah.
But maybe a guess is that the right comes then by conductor, and they want to come then by this. So right, going from conductor to discriminating is subtle. Of course, it's done by right for conductor for any abelian extension, but I think there's a subtlety because you come by discriminant.
Right, and also we're not able to at the time, yeah, at the time we're not able to handle abelian extensions in general. So there's a subtlety there.
So the Ellenberg and Venkatesh lemma. So what kind of is it? Just a pure algebraic number theory lemma? Like does there any analytic number theory input into that?
I don't think I want to know, like, take a firm footing on that, just off the top of my head. But it's mostly mainly algebraic. Yeah.
You can also just conquer when
All right. Thank you.